Recording is on.
Okay, good morning everyone. So last week I am going to repeat again. So last week we discussed about building a min heap using array, which has bottom up heapify, top down heapify, and now we are going to, and also we discussed about kth smallest element, right? So we want second smallest, or third smallest, what are the main advantages basically, right? So we discussed about these two, and we are going to discuss about max heap today. So how it is different from min heap. And so one of the examples of the implementations of the min heap is the stocks. In the stocks we have the price, and we also have 52 weeks lowest rate of the stock, and 52 weeks highest rate of the stock. So lowest is 6. Let's say the stock value is 1000, and in last 52 weeks, in last 1 year, the stock went to the lowest is 600, and in the last 1 year the highest value is 1500. So see that this is the first one is, by using min heap you can maintain the lowest value, and by using max heap you can maintain the greatest value or the bigger value. So as the value is changing every day, this value will pump into these tables, this kind of heaps, either min heap and max heap, that will automatically put the value in the correct location of the tree. Okay, this is one of the real life implementation or the usage of the heap. There could be a lot of other usages. This is one of the uses in the of the heap. So let's look at the max heap. So the just opposite of min heap, max heap is just the opposite of min heap. So max heap, top will be the max, and the next max will be in the next level, right? So the advantage is you will get the maximum value immediately with order of one. You don't need to do any shuffling or anything. Just to get the max, it just it will give you the value. Of course, if you want to remove the value, you need to rebalance, or what is that, heapify. You need to do the heapify, but getting the value is just order of one, right? You're not removing, but you just want to know what is the value here. That just order of one max value. So that's the main advantage. So before diving into the problem, so here is the problem, right? So finding the, this is last week we discussed about building min heap and finding kth smallest. So how did we find last week? So in the min heap, so what we did, like we have some values, okay, we have some let's say 100 values. What we did is we want to find, let's say, fifth minimum value. What we did last week, can anyone explain what we did? We got some values in an array and we want to find fifth minimum. Karinya, what we did last week?
No, Suresh, I'm not sure about this. Please.
No, last week we built a min heap, right?
Yeah, yeah.
First step what we did is, this is a given array, right? Given array is random order. The numbers are not in a sorted order. So what we did, Arvind, did you remember what we did last week?
Yeah, I think we started taking element one by one and started comparing uh, with the node value and then either of its children value, and then accordingly we proceeded to store that depending upon where the value lies of the.
Yeah, that's right. So basically we took each value from the array and we build a mini heap, correct? So basically we are putting in a once you put in mini heap, it will automatically do shuffling and everything. Make sure when you put first value, it will create a root. When you put the second value, it will put at the right place. Base, it will compare and it will put that to the right place. When you put the third value, it will do all the comparisons and it will create the proper mini heap, right? And if you put the fourth value, it will
Yeah.
put somewhere and it will shuffle the value. So basically you are building min heap with all these values, correct?
Yes.
That's the first step. But that won't give you the fifth minimum. This is the question. Question is fifth minimum. So what we did last week after that, you build a min heap, and you on the top you have the smallest number, and there will be a lot of other numbers in the, like all the let's say we have, this is like 100 elements. There will be heap with all 100 elements. So then we found fifth minimum How did we find?
We first find the minimum, then we remove it, then we repeat the process 5 times till.
Exactly. That's a good thing. So what we did is we build a min heap. We know if you create a min heap, the toppest element is the smallest one. So we just we removed smallest element 5 times. Like if you want kth smallest, so you remove k elements from heap, right? If you are keep removing k elements, what happens after k times? The kth element is the minimum element, right? When you remove first element, automatically the next minimum, whatever the next minimum, will go to the top, right? And if you remove second element, that will go, and again next element, whatever the minimum, will go to the top. So that's how it is, right? We do all the bottom heap and everything. So you're removing k elements, and finally after k you stop and you return that element. Hey, this is your fifth minimum, or whatever the minimum you want, right? Karina, did you remember that? You want me to show again? Here is the code last week.
Yeah.
Right. So this is what we did is we created, this is the 6 numbers, or 6 numbers here. What we did is we created heap. All 6 numbers we are inserting in the min heap. We are blindly inserting all the numbers in the min heap. Okay. Now after that, here is the thing. Of course, we did like in the middle, like we removed an element and then we added back. So again, so I removed first element, first minimum is here, and remaining heap, and then I'm inserting the minimum value back into the heap. Now it's samely, like by the time you come here, exactly same values will be there. Let's say we build a heap for all the 6 elements, and then what are we doing? You want to get the kth smallest element, call get k times now. That's so k equal to 4. Okay, kth smallest equal to 0. We are putting like 0 for the initial assumption, and then we are doing 4 times. Okay, min heap dot get. If you say get 4 times, what will give you is it will give you the 4th value, the last value. So if in case let's say k equal to 1000 or k equal to 100, in case at any point, right? Because you are having only 6 elements. But if I say k equal to 20 or 30th smallest element, we have only 6 elements. That in that situation we'll get an exception. Heap is full, or it may not be. If heap is full, it will be just 0 only, or the k is greater than, okay, k is greater than number of elements in the heap. That's what we will get this error, because you have only 6 elements. If you are asking like 20th element or 30th element, it will give an exception. Okay, so otherwise you will get the value. Kth smallest value is this one. So you remember, right? I can run again and show you. See this one. So we created a heap with this is the building the heap. So we created min heap, minimum value at the first, and then 2, 5, 9, 3, 8. This is the min heap for the given array. The given array is like this: 9, 8, 2, right? So we got the minimum heap like this: 1, 2, 5, 9, 3, 8. So next, after inserting 1 again, so we'll get the same thing. Here is the thing: 4th smallest element is 5. Right? So it will remove 1, it will remove 2, and it will remove 3, and then it will remove 5. That is the 4th smallest element. Correct? And what are the remaining values? Just 9 and 8. So 9 and 8 will be in the heap. Correct?
Yep. Yeah, Suresh.
So this is let's look at the drawbacks of this algorithm. So the today's algorithm is same thing: find kth smallest value. This is also find kth smallest value, but here we used min heap, and here we used max heap. So I don't want to explain why. I want to explain why we are going to use max heap. So before even going into this problem, let's look at what are the drawbacks of this problem. So let's look at the complexities of this problem. What is the complexity of this problem? So how did we find it? First step is build min heap all n elements. First we did this, and we got an array with n elements, right? Say so. What we did is we build a min heap, right? We build a min heap with all the elements, with all the n elements of the given array. Next, what we did, we remove. So what is the order of this one? This particular method, building the heap. So you took n elements.
Order of n.
Yeah, order of n. You can simply say order of n, because of course it's more than that, because you are taking elements from array and you are putting in the min heap. The min heap will take you every time you are putting an element, it needs to bottom up heapify, or it needs to do top down. That kind of heapify also need to do. What is the complexity of that heapify method? Any idea?
Of
Order
n
of
square.
And what?
N square.
N square? No, it's not comparison. That's what I explained last time. So when you are inserting an element, when you are removing an element or inserting an element, you just will shuffle that particular path. It won't, like, it will, as I said last time, right? Let's say you are inserting an element, it will just compare which one, either of these two values go up. You don't need to compare with all the elements in the tree. It will only compare with the particular path. If you are inserting an element, if you are removing an element, right? So we last time we discussed about it. So if you are going in a particular path, that means like kind of it make at max it will go all the way to the leaf level. Sometimes it will just stop in the middle based on the values. If you are inserting a value, that will come only here. It is this is smaller than these values, then it will stop here, because in min heap the minimum values on the top, right? The maximum values in the bottom. So if you are inserting a value, let's say you inserted a value, let's say L, the value is L. So if the L is bigger than these two values, it will come down. Let's say it comes here, L came here. Now this is bigger than this value go up, and L comes here. Now these values, these three values are bigger than L, then we are good. We no need to swap anything, right? This is smaller, L is smaller, and the remaining values are bigger, which is good. That's what the main algorithm or the rule of the heap, min heap. Min heap means smaller values on the top and the bigger values on the bottom. So it will stay here. It won't go. But in the worst case, if you are adding a really big value, if you just added a really big value here, that will go all the way to the bottom.
O of log n.
Exactly. That's what I want. Log n. At the worst case, you go and swap all the values, and the value you inserted will go all the way to the last level. It could be here or here, because you're adding a big number. The big number means it has to go to the bottom of the tree, right? In the min heap. Arvind, you following, right?
yes,
So,
Suresh.
the log n. This is order of log n. So at worst case, you are adding elements. Every element you are touching may do order of log n times the worst case complexity. This is of course this is a kind of, you can think of as order of n, because this is a kind of smaller. You can what is that? You can ignore the smaller value if you have bigger value. Here is order of n is big value. You are touching every element of the array. So simply you can call order of n. So you are building a heap, right? Now, what are we doing? We build a heap with all n elements, and then in order to find kth smallest value, what are we doing? We are remove element from the heap. How many times? K times, right? Right? So you're removing elements k times.
Yeah.
Okay. Each time if you remove, what is the complexity? If you're removing element, let's say now coming back to the min heap, you removed an element from the top. We already discussed about it. What is the process of heapify? If you remove an element, what we do? We'll put the some of the leaf value, this value back into this top, and then we will do top to bottom heapify. Correct? If you are inserting at the bottom, you will do the bottom up. Sorry, last time I discussed like here like this. If you are inserting at the bottom, it will go all the way to the top. But if you are inserting at the top, that will go top to bottom. So once you remove the value from the top, you put the last value on the top, and then you do the bottom down, like top to bottom heapify. Correct? Worst case, what is the complexity of that algorithm?
Order of n when the tree is skewed.
Tree squid. Okay, tree squid means like this, right?
Yeah, like, yeah, yes.
That's a good question. Order of I think it's order of log n. In the worst case, no, I think heap will not be like this if I remember correctly, because heap would not be like this, because we are putting in an array, right? We always put it in an array, and we always make sure it is in a balancing way, right? See, it could not be in a squid, or this is in a normal tree data structure. It could be like this, because let's say you have 3 elements, right? You put here, you put here, you put here. So immediately if you're adding an element, you do the shuffling and you make sure the tree is like this. It never be like this. If you want to do like this, one element here and one element will be here and one element will be here, because that's how it is, right? This child is here and this child is here. You are not adding in the random positions. You are adding at the sequential position, and you are doing a proper shuffling.
Okay, so that means that heap should always be balanced. Like,
Exactly. Yeah, heap will always be balanced, because you are representing the heap in an array, and you are adding a value at the last or at the beginning, and then you are shuffling here itself. Make sure these are in a proper heap formula is maintaining between these elements. So it will always be at least balanced, or at least maybe one element will be on that is also still balanced, right? If you have something like this is also balanced, not a problem. Just one level of increment on one side is not a problem. We discussed a couple of weeks ago, right? So heap is always balanced. You never be like squeezed elements or something like this. So in this situation, what is the complexity of removal? So now we are discussing about removing an element. At any point you remove the top, and then you put the last element on the top, and then you do the top to bottom heapify. What is the complexity of that function? The whole thing. Removing top is very easy. Order of 1, right? Just remove. Just already top, just remove. And then inserting the last element to the top. That is also order of 1. You know what is the last element, and you just swap it. You put it here. That is also order of 1. No need to do any loops. But now you need to do the top to bottom heapify. What is the complexity of that? The worst case complexity.
order of log n then.
Exactly. Yeah. Simple. It could be either bottom up heapify or top down heapify. Both are order of log n, because we are not comparing with all the elements. If you are comparing with entire all the elements of the tree, then that is order of n. But you are not doing it. That's the main advantage of heap. The main advantage here is no need to compare with all the elements. You just compare with whichever is the smallest, that will go up, because this is a min heap, right? In the min heap, take the smallest and push that down. I'm sorry, take the biggest element. This is L is biggest. As long as it is big, push down, push down, push down. But as long as you find the correct place, let's say the other elements are bigger than this one, then you found a good placement. You no need to do. So it's order of 3 at this position, 1, 2, 3 only. Order L stays here, but in the worst case, it may go down again because that's a bigger element than any other in this path. It will come back here. You remove element here, and finally that element goes here, and it will come back and settle here. Right? So order of log n. So now coming back to here, order of log n, and how many times you're doing? So order of log n for one time.
One time.
So you are removing how many times you removing?
O of 1.
Yeah.
Oh, sorry, O of k. Yeah.
So the whole process we are doing k times, right?
Yeah.
You are removing k times. Every time you remove element, you do the heapify. Correct? So then total will be k into log n. Is it correct?
Yes.
So you are removing k times, and every time you remove, you do the whole bottom up heapify. You can also think, because like we are doing what we do top down, sorry, not bottom up. You remove the top, so remove top and do the top down heapify. So that is the problem here. So this is the whole complexity of this, right? So order of n to build the heap, and k into log n to remove the to get the kth smallest element. Now what is the total complexity? Is the total complexity? You just sum those two
Total
things.
complexity to remove an element, or
The total complexity of the whole algorithm. So there are main
O
two
of
steps.
n plus k into log n.
Log n. So now what you do? You always take the big value. What is the value? Total complexity could be
O of n.
O of n. Yeah, because you're already doing O of n. So if n increases, if n is 1,000 elements, you are iterating 1,000 times. If n is million elements, you are iterating million times. So basically the complexity increases as you are increasing the value of n. Right? The space. So the time complex. This is the time complexity. Total time complexity. So it is order of n. Like it will, of course, there is additional value here. Not only order of n, it is greater than order of n, because every time you also, like after order of n, you're also doing like k times you are removing elements. So definitely order of greater than order of n. Okay, so maybe you no need to mention that this is the actual complexity, because it will increase both, right? It will increase the, if n is increases, it will also increase this coefficient. So even k increases, that is another problem here. So let's say we have n here, and if k increases, that means you want you have 100 elements, and you want 99th minimum. You added 100 elements and you removed 99 elements. It's what, like, kind of, do you see the drawback here? You added 100 elements and you removed again 99 elements because you want 99th minimum. So it's like doubling. You're unnecessarily adding. There is unnecessary component here, but let's see how that can be reduced. Okay, so let's look at another problem here. So not only time, what about the space complexity? Anyone can guess how much space are we taking up? So this one, we are building a heap, right? So you took n elements, and what is the space how much space we are taking up to build the min heap?
Order of log n.
Space. How much space you want? You have CD disk.
O of n.
Exactly. So you have simply you have books. You have a books of different sizes. I gave you 100 books. Okay, I'm asking you to put in such a manner smallest book on the top and the next smallest on the bottom, and you do whatever the manner, like very biggest book size wise or number of pages, let's say size wise, the biggest book on the bottom of the whole pile. So how much space you need? If I give you 100 books and you are taking the 100 books and arranging in a different manner, but you just need again 100, you need a space to put all 100, right? You got it, Arvind? Why it is order of n?
Yeah.
Again, you need exact same space. So let's say you are not. So let's say the ask is don't change the existing array. In some cases, we don't want to modify the input. Sometimes you want to maintain the input. Like in the some of the algorithms, you can take the array and you can modify the array. In some of the algorithms, they will say, oh, this is the input. Don't change the input and put it in a different, the different shelf. Don't that you don't change the input. So you are putting in a different shelf, let's say. Okay, so that means you already having order of n here with the given input order of n elements, and you are taking another order of n space to create the whole min heap. Okay, so now the space complexity order of n. Do we have any other elements? For the second one, are we taking any extra space? We need kth smallest. We are taking a small extra space.
Stack.
But can't we consider that as like constant?
Constant, yeah, of course, constant. You are saying stack, Karan. Where is the stack here? In our algorithm, where is the stack?
No, Suresh. No.
We did not take any stack, right? So first,
Yeah.
in order to build a heap, this min heap takes order of n space, because you are inserting every order, all the elements. If I give you million elements, you are inserting million elements into the min heap. And of course, after inserting million elements, you are just, let's say I want fourth smallest. You are iterating just 4 times. Space complexity is just constant 4 times, but no, time complexity 4, and every time you remove order of log n. But how about the space? You are not taking an extra space, just only one small integer, which is a constant. Even if million elements, I will take one variable. Even if it is 2 million elements, I will take only one variable, because you need only kth smallest. Based on the requirement, I don't need any another variable, right? This is another just variable k equal to 4, another variable the kth smallest. So these two variables are constant irrespective of the size of the input. So that's why it's a constant. You don't need to consider those. So that's why the maximum complexity is space complexity of this whole algorithm is order of n. Okay, so now the main advantage of this one, the min heap, building a max heap. Let's consider that. Let's consider what is the main, how we do is little different. We will build a max heap. We have to build a max heap. But we need to see the main drawback here is you are building the max heap or min heap for all the elements. We need to see whether that is required. How can we optimize that? So you are building in order to find a fourth element. Let's say you have a million elements. You want fourth minimum. You are building another min heap for all the million elements in order to just find fourth element. That's where the funny thing happening. Why do we need to build that? Is there any better way of doing it? Can you guys imagine or any come up with any idea? Let's put the input, then we will figure out. 982135. 982135. Okay, 982135. So you want fourth minimum, right? Fourth min. Let's say fourth min. What is the fourth minimum value?
5.
Exactly. Because this is first. You can just look at here. First minimum second minimum, third minimum, fourth minimum, right? Right? So in order to do this, what are we doing here is we are building the whole in the previous algorithm, we are building the min heap for all the elements and we are removing 4 times. Now let's look at the other way. Let me see how can I explain is basically okay, let's come up with an example. I want to give you the main idea here. How are we going to do with the max heap? So let's say you have something like 100 elements like this. 100 elements we have. Okay. So now we want fifth max, fifth min. Sorry, we want fifth min. Okay. Fifth min. What is fifth min is, let's say all these elements are first the input is not ordered, right? This is just random number of elements without any sorting order. Now with a, let's say you're building a min heap. Okay, let's say you're not building a min heap, you're sorting the array. Just imagine you're sorting the array and putting the small to biggest. Just imagine. So now this is a sorted order, SO, sorted order, and here is the minimum, here is the next minimum, and these are the values. Now where is the fifth minimum? 1, 2, 3, 4, 5. Here is the fifth minimum, correct? Right? Now let's look at the
Yes.
let's look at what is happening here. You want fifth minimum. Let's look at all these 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just consider these things. This is the fifth minimum, but what is the other inherently you can find what is the other property of this one. This is the fifth minimum in the whole 100 elements, but this is the maximum of these elements. Look at that. That is the main concept here. That is the main understanding we need to find. This is the maximum of rest of the elements in this block, correct? Is it right or wrong? Because you already put it in a sorted order, correct?
Yeah. Yes.
So this is the max of the elements which are before the fifth minimum, before the kth. You want kth minimum, but remaining elements are smaller than this element what you are looking. Now let's look at the idea here. So if you keep this block, that means this is the block where I am maintaining. You have 100 elements, you have million elements, I don't care. But if I am maintaining this block of k, you want kth minimum, this block of array or block of some data structure which will put the k in sorted order or in some order where I can easily find what is the max. You are putting in some data structure where it will give you the max of this elements, k elements. What is the data structure which will give you the max element in order of 1 with k elements? What is the data structure?
Array,
Array?
simply.
Array,
Yeah.
unless you sorted, you cannot find an order of 1.
Yeah. Okay.
You want
Sorry, hashing.
hashing.
It's
Hashing is good, but
map.
hash requires
Sorry,
hash.
I was connected to
Map or hash is good, but it requires key value pairs. It will require additional key, like kind of you need space of order of 2k, because you need key, you need value. So what is the data structure which will give you max value with order of 1? Hey, give me the max. Take it with just order of 1. We discussed last week. We discussed about a data structure which will give you minimum element with order of 1. Just this is data structure which will give you minimum value immediately. What is the data structure? We discussed about data structure last week. What is that item we discussed?
For which, Suresh, which will give us.
So last week we discussed about some concept, right? That will give you the minimum element with order of 1 without taking any extra time. It will give you order of 1.
Min heap.
Min heap. Min heap, HEAP. So now we are asking a reverse question. We want a maximum element. We want kth. This is like fifth minimum in the whole array is fifth maximum in the small subarray. Is it right? So here is the fifth. You want fifth
Yeah.
minimum. You want fifth minimum. Very complex here. Try to understand here. Fifth minimum in this whole 1000 elements is equal to fifth maximum in this small subsection. Correct? That is we are changing the problem definition in a different way. So you want this maximum with order of 1. We don't want to do any computations. Put all these k elements. Put all these k. This is, let's say, kth minimum. Put all the k elements in some data structure, and I want with the order of 1. I want that max. What is that data structure? If you want min with order of 1, you use min heap. If you want max with order of 1, what we do?
Max heap.
Exactly. That is why we are using max heap. We don't want to put, of course we will put in an array, but it is not normal, it is not sorted array. This is an array which will build the max heap. So you put the elements in a max heap manner. If you put the elements in a max heap manner, then the 0th position is actually the maximum value. Always maximum value, correct? The value here will be the maximum out of remaining k elements. You understand, Karanya? Are you following so far?
Yes, Suresh. Yeah.
So basically, if you are asking kth minimum, we will create a max heap. We will create a max heap of k elements in the form of array only. We don't want to sort all the elements. If you are sorting, the sorting algorithm, order of n square, order of n log n, like a lot of other sorting algorithms. But here we don't want to sort all the elements. What is the point? We don't need to sort. They are not asking like give me the sorted order or anything. They are asking only the fifth minimum. That means which is the maximum value out of these k elements. So by building a max heap, you are able to find the kth minimum. But what is the advantage here? The advantage here is you are building only max heap of k elements. Correct?
Okay. First
You are
5 elements. 1, 2, 3, 4, 5.
exactly first 5 elements. You are not
Yeah.
building the max heap of all the elements. You're saving a lot of memory here. But you can ask like, is it right? Is it right if you are taking only first 5? Let's say these are the integers. We have 5, 10, 15, 20, 30 something, and you have a 2 here. This is, let's say, 2 here, and there will be, let's say, 7 here. Let's say this is the fifth maximum. 7 is in the fifth maximum, but you are not putting the 7. 7 is the actual value in the whole 100 elements, but you are not even putting 7 here. You are just taking first 5, and then you are putting in a max heap. And are we going to return this? Are we going to return this is the fifth max? No, because it's not a sorted order. Like this is the input, and this is not the input. If it is sorted, you don't need to build anything. You just go ahead and order of, if it is a fifth element, a array of 4, 0 to 4, right? 0 to like 0, the index starts with 0. So if you want fifth max, order a of 4. If you want 10th max, a of 9, right? What is the point? Like if you already sorted, everything is sorted, you don't need to worry about anything. But if it is not sorted, this is the input. What we do is, first we will take the k elements and build the max heap, then we do the magic. What is the magic here is, it is very carefully understand here. So what we do is, we already created a max heap. The max heap will give you the maximum element here, right? Now what we do is, we will take the rest of the values, like we'll proceed from here. We already counted k elements. We took the k elements and put it in a max heap. Next, what we do is, from k plus 1, from the k plus 1 all the way to the last element, we will take each value and compare with this maximum value here. That means, if this top value is smaller than this value, that means the top here is actually the bigger value than this one, then we will ignore this value and we'll put this value into the max heap. This is very carefully need to understand. Yeah. Yeah.
I thought you were stuck.
No. I'm just giving you some pause to understand here. Why are we doing here? So basically, if you find an element which is smaller than the root here, then we will ignore this root and we'll put this value. Basically, we will insert that. Basically, we will remove the top and then we'll put the value there, and then we will do the TopDownHepify, and it will shuffle the value properly. Basically, let me give an example. You have a very, very big school. You have 100 people in the school. You want to find 5 people based on their height. Okay, let's say you want to find a smallest height. Let's say a student with smallest height, another next student with smallest height. Okay, let's say like this. Okay, you found 5 students, 1 2 3 4 5. First you pick the 5 students. Okay, now what you do is, you thinking here is the 5th smallest, but you found something like this. You found another guy who is between these two, who is guy like something like this height. What you do, you remove this guy and you put this guy in this table, right? Just understand in a normal fashion. So you found a guy who is in between. Then what you do, you remove that bigger guy. Oh, you are so big than these 5 people. Go ahead, go to the remaining elements, and now you consider this guy and you shuffle everything to make sure they are in the same order. Now let's say this particular element, this element is something like this much height, like this much height. What you do, again you remove this element and you take this element and put it in this order. Then that guy will come somewhere here, correct? Based on the height, this guy is bigger.
Then Suresh, for each comparison, we are going to replace the heap.
Yeah, we have to do it. Yeah, we have to do it. Otherwise, you want to know the fifth tallest guy. You want to know 5th tallest guy, but you have to shuffle it. You could not, you cannot add this guy at the beginning or end. You need to add at the right position. So you just put at the root and do the heapify, and that will automatically go at the right position, and the tallest guy will come into the first position, right? But what is the complexity? Just order of log k, it's not log n. That is the main advantage here. Just very small k elements. You're not building the heap with all 1000 elements, right? That is the problem with the min heap. Earlier you created a heap with all 1000 elements, and then you are doing like every time you remove an element, it will take order of log n, order of log 1000. But now just k elements here. It's much better, right? Space wise is better, even complexity wise also better. Are you guys following so far? Did you agree?
Yes, Suresh.
How the time complexity will get better, Suresh?
Time complexity is better because you are shuffling only k elements. But in the previous algorithm, you build a really big heap. You build a heap with 100 100 elements. If you give 100 elements, you're creating a heap with 100 elements, and you are shuffling all the elements. But now you are shuffling only k elements. If it is 5, just to 5 elements, you are shuffling the values in this 5 elements array. You are not shuffling the values. You are not doing heapify top down or bottom up anything for all the 1000 elements, right? Space wise is safe. You just need a space of 5 elements. And also complexity wise also log k, it's not log n. Every heapify, every time you remove an element and you put it back, that will take only order of log k to shuffle the elements.
But Suresh, how will we select these 5 elements? Should we?
That's a good question. So we don't know how we will select 5 elements. We blindly take the first 5. We'll blindly take the first 5 elements and put them order. Just imagine that this is a school of 100 people. What you do, you want to put them in 5 people. You want 5 people in based on their height. What you do? So how can we, like, you can take one student and compare with rest of the 19, and you can take the second student, compare. That's order of n square solution. You don't want to do that. What you do is you take the 5 people and put them in order of their height, and then you compare next guy. If the next guy is in between these two, like say he's shorter than the tallest guy, and you remove this guy and put them into this array and shuffle them again, right? So you need 5 people based on their height. Okay, you found another sixth person who is shorter than this tallest guy. That means you don't need this tallest guy anymore, correct? This person will not be in this fifth smallest or 5 smallest people. You just need 5 smallest people. You already have 5, but these 4 smallest people plus this guy, you found another smallest person. Then there could be either this guy could be smaller than taller than the rest of the 4, or this guy could be smaller, or this guy could be in the middle. We don't know. Unless you shuffle them, you don't know where this guy will fit. But one thing you can remove this guy. You can remove this tallest guy for sure. There is no doubt. This guy is super tall. We don't need that. He will be 10th tallest or 50th tallest. We don't know. So we don't need to consider this guy anymore. Of course, we took with an assumption that these 5 people are the 5 smallest, 5 tallest, or whatever. But now since you found another small number, you put them in order, and by removing the tallest number, which is maximum number. Now what you do? You did that. Now you compare with the next person. What is the height of this guy? Is it smaller than the tallest person here? If yes, we'll put them again. If this guy is really small, if really tall, taller than the 5 people, you ignore them. Hey, we don't need you. Let's go to the next one. If this guy is shorter than any of these 5, let's put them here and shuffle them, and ignore the tallest person, and then take this guy. You understand the algorithm here?
Suresh,
It is complex, but yeah, go ahead.
What is the need of shuffling when we find the tallest guy, then the K? The whole. What is the need of shuffling the whole heap?
We
Actually,
need
if
to, go ahead. Yeah.
If one person is taller than K, it is not enough to replace only K, because already he is the tallest person.
He is the tallest person. No. We will only replace. We'll remove this guy if the person is shorter than this one, not tallest, right? If this person is really tall, we don't need him, because we know these are the 5 tallest people from the small, shortest person, and then next shortest, and then in the order of 0, you will have the tallest people in that 5 people. So you have 5 people. This board is really became like this, so it's tough now. So I need to erase some of the places. So basically, you found the 5 5 tall people, 5 tallest people. Now you found another guy who is in between. If you find a person who is in between, then you need to shuffle them, right? Because next time you want to compare with the tallest person. So you have people like this: 1, 2, 3, 4, and 5. Okay, this guy is like this. So now you found something. This person is somewhere here. This person is something like this much height. Okay, so now this will go somewhere here. So definitely you remove this guy, because this guy is shorter than this tallest, right? You remove this. Now you need to put this guy into the order, because you cannot place at this location. If you place this location, he will be like this. Now it is not in a search. So 0th position, let's say 0, this is 0th position. 0th position is not the tallest person. There is one more guy at the 1th location which is taller than this guy, correct? That's why you need to shuffle them, so that the new person will come here, and now this person will be in the 0th position. Now you need to compare with this person, because this guy is the smallest, this guy is the tallest. Let's see if you find any another element which is smaller than this guy. Are you guys following so far?
Yeah, but Suresh, I'm wondering that ultimately we will be doing the same number of comparison, right? We will be checking through
Exactly.
all the elements.
Exactly. There is no way you can find, unless you traverse all the elements, there is no way you can find small number. Let's say any question. Let's say you want to find small number of n elements. You need to compare small number of. If you want to find big number, you need to go with all the numbers. How, without reading all the numbers, how would you know what is the value here? Smallest. Let's say you want first smallest number of 1000 elements. You need to look at all the values. You want to know the bigger element in the 1000 elements. You need to. There is no way you cannot guess a number. There is no way complexities cannot be less than order of n for sure. Unless you read the value, you don't know whether that is smallest or bigger. We are not reducing the time complexity much. Of course, we are reducing little bit, but we are reducing the space complexity here. Look at the space. How much space you need? Just k elements. You just need, even it doesn't matter if you have 1000 elements or million elements. We need a space only for the k. If you need, let's say you need 100th element, or let's say you have 1000 elements and you want 50th smallest. You just take an array of 50 elements, heap of 50 elements, right? You are not taking the 1000 elements heap, and you are not putting every element in the heap, right? You are only putting kth element, k number of elements. You got the advantage here?
Yeah, Suresh.
Yeah. Space wise, it's a space wise. We are trying to find a space complexity. We are trying to reduce the space complexity. Sometimes in some of the problems, you cannot reduce time complexity much. You need to see how can we optimize. When we write in any algorithm, we need to find how can we optimize. Optimizations can be done either time wise or space wise. You can reduce the time, and that way it's time complexity. You are optimizing by time. If you remove the space, you are using less number of data structures or less number of elements in the data structure. Then it's a space complexity. You are reducing the space. Let's say if Karnya used a heap for this, or stack, you are using heap and stack and another array. You can use it if you want. You can use unnecessarily. You can use any number of data structures, but we don't need stack here. We don't need queue anything. We just need a small heap. But in the previous algorithm, last week algorithm, you took a heap of n number of elements, and you are putting everything in the heap, and then you are taking 5 times. But here we are reversely doing. We are, instead of even though you want 5th minimum, even though you want kth minimum, we are creating a max heap. So basically, that's a small slight understanding. 5th minimum is the 5th maximum in the sorted array. That is the reversely understanding. Let's say 5th minimum in a normal array is equal to fifth maximum in the sorted array. That means you can take a max heap of k elements. That's it. That's the main logic here. Got it? So we can run with this example to run this problem, how we are doing with this. Shall we go and execute this problem, the 982.135, to understand
Yes.
better? Then you will get full understanding, right? So 982.135. Aranya? 982.135. So we
Yeah.
need a fifth min. We need is it fifth or fourth? Let's look at the algorithm which I wrote so that it will be easy to understand. So here is the max heap, and yeah, let's say third. You want third. Okay. You want third minimum. Oh my god, it's already 9 o'clock. Huh? So you want third minimum. That means you just need to create a heap of 3 elements. That's it. Even though we have 6 elements, we need heap of 1, 0, 1, 2. Okay. Heap of 3 elements. How do you do? What you do is you will put 9 and put the 9 in the heap. That means heap will be 9 here, 0, because at the beginning there is no elements. You put 9 at the root. Now you read. So we will read only 3 elements. Okay. Now 8. Put the 8 in the heap. Put 8 in the heap. That means 0, 1. So 9 here, 8 here, 0, 1, which is good, right? This is the max heap, which is still following the rule. Top is max and bottom is smaller. That's good. Now 2. Let's take 2. 2 will go here, which is also good, right? You don't need to do any heapify or anything. It's already maintaining the max heap formula. So you're putting 2 here. Now what you do is you stop building the heap because you want 3. So this is the third maximum. You are thinking, hey, this is the third maximum, take it, but not. This is not the third maximum. What is the third maximum in this whole input? What is the answer here?
Third maximum is 2.
Third maximum
Is that what?
In the input. Here is the input.
The first.
What is the third maximum here? First maximum.
Third max is 9.
5.
Oh, sorry. We want min, right? Third min, sorry. And yeah, third max is 5, but whatever. So we want third minimum. Sorry, I'm asking max, not max. We want kth minimum, right? Let's say k equal to 3. So we want third minimum. What is the third minimum?
3.
3.
It's 3.
This is first minimum. This is second minimum. 1, 2, 3. So the final answer is 3. But if you are building a max heap of 3 elements, now can we say 9 is the answer? No, because this is not third minimum. This is not third minimum. We want third minimum. What we do is, as I said before, you completed scanning these elements. Now you scan each element. Let's scan each one. Let's scan 1 and compare with the root. Okay. If you find a small number, the rule is like this. If you find a small number than the root, remove the root and put that value there. That means you remove the 9, put the value 1 here. You know that whenever you remove the root, or if you, it's almost like you are taking the root and putting the value someone there. If you are putting some value there, what you need to do is you need to do the TopDownHepify. Always do that, because if you are changing any value, if you insert the value, you need to do the BottomUpHeapfy. If you are changing the root, you need to do the TopDownHepify. This is very common operations of the heap. If you are, let's say, NQ, DQ, this is a Q, you have NQ, DQ operations, right? So what you do in that, you do whatever you want. Finally, you need to maintain the Q. Similarly, heap, you are inserting an element at the root. The heap has a different thing. You can insert either at the last. You can insert you can replace the root. That is the thing, right? So when you're initially doing, you inserted 9 here, you inserted 8 here as a leaf, and you inserted 2 at the leaf, and you do the bottom up heapify. You are inserting at the last elements. You are inserting at the leaf nodes. You need to do the bottom up. But if you are inserting at the root, you can inserting or removing the root and replacing the value at the root, you need to do the top down heapify. So why are we doing? Because we need to shuffle the values, make sure the third minimum, there are 3 values here, third minimum should be on the first element. That's what the main purpose here. So if you look at 9, 8, 2, sorry, not third minimum, third maximum. So if you look at 2, 8, 9, 9 is the third maximum here, right? So 9 is the third maximum in this 3 elements. But if you look at like this, if you are replacing 9 with 1 here, so we have something like this: 1, 8, 2. Is it the third maximum? Is it third maximum? No.
Recording is on.
Okay, now recording is on again. So you removed the top element and you inserted 1 there because 1 is smaller than the 9. But you need to do the top down heapify. Otherwise, you will in a wrong position. So it's 1 is not the third maximum. We want third maximum in this array. That means you need to do the top down heapify. If you do the top down heapify, 1 is here, what number will go to the top? Did you guys remember the top down heapify algorithm? This is a max heap. Max heap means what we need to find the maximum value. If it is min heap, you need to find the min value between these two, that will go up. If it is a max heap, you need to find the maximum of 2 values. What is the maximum of not only 2, maximum of all 3 values? It is 8.
8.
Exactly. So what is the maximum value? The 8 will go to the top and 1 will go to the bottom. So it will be like this. What happened? Okay. So it will be like this. 8 will come here, 1 will be here, 2 will be here. That is the top down heapify. Finally, this is 0, 1, 2. So now 8 is the third maximum in the given values, correct? Now we are done with 1. Now you got the 3. Again the same thing. 3 is smaller than the 8. What you do? So the heap is like this now. 8 is here, 1 is here, 2 is here. So you remove the 8 and put the 3 there and do the heapify. So now 3, 1, and 2. So 3 is here, 1 and here 2. Do we need to change anything?
No.
Because this is maintaining the max heap property. Max heap property is saying root is max. Yes, root is max. Go ahead. Now you're done with 3. Now you compare 5. Is 5 greater than the root? Sorry. Is 5 is smaller than the root? Yes or no? No, because you just ignore. Hey, we need third maximum, and you are giving like 5, which is like greater than this. This guy is taller than the tallest people here. This is the third tallest. This is the small. This is the next small. This is the 3. So we already found third tallest in the given people. Now you are saying 5. This is like this. We don't need that 5. Just ignore it, and let's see the next value. You go on until you complete all the values. Now you completed all the values. There is no more values after 5. That means you scanned all the elements. Now what you need to do is you want third minimum, right? Third minimum is simply the third maximum in the max heap. Just give the root value. 3 is the answer. You got it?
Yeah.
So basically third minimum is just the third maximum in the heap. This is the max heap. You know that this is the maximum value than any other value in the down. You don't need to look at any other. Simply third. Top. You just return the top. So the main advantage here is the space wise. space wise, you just look at it, just 3 elements. You are not taking the whole 6 elements. That's the main advantage here. Okay, it's already 9:07. If you guys are understood, I can show the algorithm itself. Are you clear? Or any questions so far? Is it clear?
Yeah, Suresh, clear.
It's very like a simple array manipulations, but a lot of logic in this. So that's why it is taking it. It took this much time to explain, but it's good actually when we are deeper going into the deeper understanding of each and every concept. That will build you a lot of confidence, and that will give you like kind of you can also come up with a new idea when you are interviewing, right? When you are in the interview, you will come up with a new idea with this kind of algorithms. So we got this same thing 92, 912, 945, or maybe a little bit different numbers here. That's okay. So 192, 945. We want third minimum. What is the third minimum here in these values? Third minimum.
4.
4, right? Let's see. We get the 4. So under 0th, let's say 0th minimum. If it is 0, you can take first value. That's okay. So now what are we doing here is we took the okay, so this algorithm is just I'm building the first one. I'm building the min heap. Wait, I'm doing max heap here. Just let me call it max. Is it like shift, or let me rename symbol? Not min, max, max heap. So come on. So I'm just doing max heap. So let's look at the first algorithm. So I'm just building this is for building the max heap. This is the first algorithm. Basically, you got the A, and first algorithm is build max heap of all elements. This is not the actual algorithm, just kind of how to build a max heap. So you can display the max heap here. Now we are doing another algorithm, find kth minimum using max heap. So this is the thing. So this is the main algorithm we want to discuss. So here is the input array, which is not sorted. Okay, and here is the k. If the k dot length is 0, array is empty. You can't do anything. If the k is greater than a of length, this is all the boundary conditions you need to write. In interview is very important. If I'm giving you 10 elements, if I'm asking 50th maximum, what is the point? Wrong k, wrong input. You're asking a 50th max, but you gave only 10 elements. So the k is bigger than the length. You send wrong k. If k equal to 0, if some case, k could be 0, then we may have to return the first maximum, first minimum. So making it as 1, just kind of another input. If someone says if k equal to 0, return the first element, then I'm just marking as k equal to 1. So the first step here is build a max heap of the first k elements. I told you, right? We need to build the maximum heap of k elements. That means all the way from array of 0 to array of k minus 1. That is the k elements, right? You just start with 0th element all the way to the k minus 1 of the given array. Okay. What is the order of k is the complexity. So max heap, and you are iterating k times I equal to 0 to I less than k, and you are inserting in the max heap. So the max heap is the class I built here. It's exactly like the min heap. I don't want to explain here. It's same thing, bottom up, swap, and everything. Only conditions will change is this one. The max, instead of finding the min, you need to find the max, and you need to replace the max. So carefully understand. I will send the code. So we look at the side-by-side comparison with min heap and find out the differences. Okay. So this is also same thing. We need to compare with parent. If the parent value is smaller, and if you are inserting, right, it's always do the same thing, swapping, but based on the values. So this is the whole max heap. So I'm not going to explain each and every function there, but you build a max heap and you're inserting k elements. Now new max heap is created. Now for each element after kth element, that means array of k to array of n minus 1, compare it with the root of the max heap. So what are we doing? I equal to k, I less than a dot length, I plus plus, get top. Get top is the method which will give you the top element. It won't remove it, it will give you the top element. Okay. Hey, if the top element is greater than the next one, that means this top guy is taller than, this top person is taller than the person you are looking after k. You started at k all the way to n minus 1. So if you find a small number, you just replace the top. Replace the top means this is a method which will replace the top. Here is the thing. This is the top value, and a of 0 equal to top. So you are overwriting the 0th value. That means you are putting at the top, you are putting at the root, and you are doing top down heapify. I told you, right? When you replace the 0th value, you need to do the top down heapify. If you are inserting at the bottom, let's say here is another element here. Insert always does at the end. See this? Current is represents the last index where you can insert, and you do the bottom up heapify. You need to do from bottom to the top. If you are inserting at the end of the tree, if you are inserting at the top of the tree, this is the top. You need to do the top down heapify. You guys get it? So there are two methods here. Get top is there, and get is there. Get will remove the top, and get top will just give you the top element. Get top is something like, okay, here is a of 0, take it. I'm not removing the top, just giving you the value. What is the value? It's kind of stack.peak. You guys know that, right? Stack.pop and stack.peak. Peak will give you the top element. It won't remove the top element from the stack. If you say stack.pop, it will remove the top element and give you the value. Similarly, get top will give you the top. Okay. So what we did is we compared with the top element. If the top element is taller or bigger or greater than the element you are looking in the array, in the input, you are replacing it, and you do the replace for all the time, for all the elements when you find it. And finally, the root of the max heap is the kth smallest element. You are just saying here return mh.getTop. That is the value. You guys following so far?
Yes, Suresh.
This is very complex. The trees and graphs are very, very complex. You need to put full focus. Every line you have to understand, everything. Otherwise, you will fall apart. If you did not understand one step, please tell me. Otherwise, there is no point of explaining the rest of the steps. If I am even
Actually, we constructed it as a whole, Suresh, but to start with, we have to construct a heap first, and then we have to start building upon one after the other. That's how I can accomplish this. So
yeah.
The whole program is so long, and the concept is also a bit complex.
Exactly. Yeah, very complex. That's why I'm saying we can do one thing. Like, since it is complex topics we are maintaining, I can give you more time if you want. Hey, we are both are working, we need more time. Take maybe I can skip next week. You guys can look at this min heap, max heap, and understand. Use this time next week. You can use this time to practice rather than take it. It's tough to allocate another time, I know. So maybe what you can do is you both can join the same meeting if you want, and you can explain each other, and you can practice each other, and look at each line. You can also debug, right? If you have a C#, I think this particular GDB online will allow you to debug. So you can put breakpoints, and you can also debug. Actually, I don't know whether this will support, or you can convert this into JavaScript, other languages, and you can also debug. Right now, C# is not allowing debugging. So you can see where you stopped and what is the values, right? So there are other ways you can, or you can do the pen and paper. Just take a pen and paper and iterate the values. So that way you can get into the bottom of it. We don't want to proceed unless you understand completely. Basically, I don't want to take the quantity is not important. Quality is important, right? Even though you practiced 10 in the particular just trees concept, those 10 algorithms, you need to know bottom of it, every end to end. You need to understand every line of code, and then you will get full confidence of the topic. Correct?
Yes.
So I'm happy to do that. Like maybe next week, if you want, I can skip it, or
Yeah,
maybe,
we'll work with that, Suresh.
yeah, or maybe what I do
It
is I
will
will
be
just
better.
listen. I will be the listener. You come and you explain what you understood, how the min heap working, max heap working. If you want, you can. This is very very popular algorithm. This kth smallest element is very popular. Even the interview which I was in this company now, Providence, where they asked this similar question, which is more complicated on top of this. The question they asked is not simple single dimensional array. They asked the question in multi-dimensional array, multi-dimensional matrix. You know the matrix, right? 2 by 2, 4 by 4, that kind of matrix. In that matrix, he asked, give me fifth maximum, give me kth maximum. I was so puzzled, like, oh my god, how to do this? It's kind of similar. Just it's another. It will be. We have to use the heap only. For that also, we need to use heap. We can also practice that if you want, but very important. The practice and getting to know the exact, depth is really important. Okay. So what we did here, here is the input. Look at the input. This is the input 9, 1, 2, 9, 4, 5, and we build the heap. I know, see, like there are duplicates here, 9 and 9. If you build the full heap, this is the full heap. All the elements like this, 9, 9, 5, 1, 4, 9. Please remember, this is not sorted array. Look at that, 1, 4, 2. It shouldn't be like this. If you are sorting the entire array, it should be like 9, 9, 5, 4, 2, 1. But we are not sorting the full element. We are putting in a heap. It will follow the heap rules. Now this is building the whole heap, but if you look at here, we are not building the whole heap. Finding the third maximum will build only 3. See, new heap 9, 1, 2. That is what the heap we created initially, right? 9, 1, 2. Oh, I took 8 here. So but you got the idea, right? So basically we build a heap with 3 elements initially. So 9, 1, 2, because it will take these 3 elements. See this, 1, 9, 2 becomes 9, 1, 2, because 9 is the max, right? Max heap. We created a max heap, and top is the maximum value. Now third smallest element is 4. Finally you got the third smallest is 4. It did all the things created. So now if you want to find the k equals 0, k equals 0 means here is the max heap, only one element. Because first element is 1, you are thinking 1 is the one, and that is the smallest, that is the first smallest element. But anyway, you found the full logic here, right?
Yeah.
We are building the heap and the max heap, and then you are taking the top value. That's it. So yeah, I hope you understood the algorithm. So I can send you the code. So this is very complex, as I said before. So if we go to the course here, course means a kind of the number of things. We did a lot of things in trees. We started a couple of weeks ago. We completed BSTs and everything, heaps. We completed heap. There is one more interesting first common ancestor. I keep pushing this. This is kind of complex algorithm. This is also very common interview question, common ancestor. I will try to explain very like 3 or 4 kinds of varieties of solving this, very complex. So I will try to explain it next week, unless if you guys want to do this one. If you still want to, like, maybe one of you can come and lead the session and explain what you understood about binary heap, min heap, max heap, how the algorithms working. You can do all sorts of things also, fine. I will be the listener, and you come and explain what you understood.
Okay, Suresh.
You want to do that, or you want me to go to the next
Yeah,
one?
yeah, I'll do that.
That's good. That's good idea. Yeah, next week we can join and you explain. You take either this one or take this. This is the the better one. Building Max Heap and how the Max Heap is working. How you're taking the. This is because this is the main question they will ask you. So if you are very smart, you can explain. You can explain this first algorithm and tell and explain the drawbacks of it without writing the code. You say, hey, there is a way to do it with the simple ways, creating the min heap for entire array, and then take kth time, take the root kth time. You will get the kth minimum value. But here is the drawback: it will take a lot of space. You just explain that, then you come up with, hey, there is another smart way of doing it by using max heap. Then the interviewer will be so impressed. You are so passionate, and you explain the first algorithm and you explain the drawback of the algorithm, and then you are coming up with the max heap, and you're explaining. So he will be so impressed. Even though you complete or not, doesn't matter. No one can write the algorithm without any errors on the first go. So if you get the interview question, this is the only code you need to write. You don't need to write the max heap. You don't need to write this entire class. Only thing is you need to write these two loops, this loop here and this loop here. That's it. Because they are not asking you to build the whole max heap. If you like, you complete this, if you complete this in 15 minutes, then they will ask you, hey, I'm curious how you going to build the max heap. If I'm the interviewer, I will say, if you complete in 15 minutes, I don't have any other question. I don't want to ask another linked list or stack or anything. I want to poke here itself, and I want to see how much you know about heap, how the max heap work, what is the bottom up heapify, what is the top down heapify. I want to know more about your understanding of the whole traversal of these heaps. So that's what I do. Like, based on the time, if you take this whole 45 minutes for this writing these loops, that is also okay. But if you can complete without any errors, I will be so happy, because you completed within 45 minutes and you wrote algorithm without any errors, and you have full grip of the algorithm, what is happening here, why are we doing this, what are we doing this, you already explained everything. So I'm okay even if you took 45 minutes and give the algorithm without any errors. But if you finish faster, I will dive into this one. Hey, how do you build the max heap? Okay, that's how the
Okay.
interview will go. Yeah. So next week you come up with the explanation. Like, you can explain why are you building it, and what are the different ways. There are finding the kth algorithm, finding the kth smallest is so many ways. The first way is very, like, even before building, you don't need to build a heap. The first way is sort the array and take the fourth element or take the k element. You have to explain that, hey, very small, very easiest solution to write is sort the array, and then take the kth element, which is simply order of k minus 1, like O of array of k minus 1. But you need to explain the drawback. The drawback is you need to sort the entire array, right? So then you come up with this approach. Hey, you can build the min heap. This is the complexities and this is the drawback. And here is the max heap solution, which is smarter, which is a better solution than other two. And you need to explain why it is better solution. And then you come up with the algorithm. Okay. So what we did here, step 1, I can write and send everything. Step 1 is build. I think that's what we already have here. Actually, in the algorithm, steps already there. Step 1 is build max heap of all the element. No. Here. Step 1 is here. Build max heap of k elements. Okay, I'm putting here. So step 1 is here. For the step 1, what is the complexity? Time complexity is order of log k, right? No, k into log, yeah. You take k elements and log k. Every time probably it will go log k, and the space wise order of log k. No, order of k. You are building only k elements, right? And step 2. Step 2 is what we did here. Step 2 is for each element. This is what the step 2. Each element after kth element. After kth element, and for each element from, I think you can something like for each element from kth element to the last element. That means from order of k, array of k to array of n minus 1, compared with the root of h, and swap if it is smaller than the root. Finally, step 3 is step 3. Take the root of the max heap, right? Return, basically just take and return the root of the max heap. That's a step 3. Finally, root of the max heap, the k smallest element. That's what the step 3. Okay, that's it for today. Any questions so far? Are we good?
Oh, Suresh, thank you for the session today.
It's really late. Thank you. It's already almost like 11 o'clock, right? Okay. I took a long time today. Yeah. Cool. Okay. Take care, and we'll meet next week then. Okay.
Yeah, thank you, Suresh.
Thank you.
Good night. Bye.
Good night.